recording.
Okay. Oh, okay. We are on the air. Okay. Jessica's bragging that she can count backwards. Okay. All right. so, so we were just saying for the do now, you're given a graph of the position. The first part you're telling, you have to determine where the position's positive, where it's above the x-axis, and where it's negative. But the second part, where is the velocity positive? Velocity is the derivative of position. So you have to look at the slope of position, see where it's positive, and where the slope of the position graph, where the velocity is negative. So the first derivative is just the slope. You look at the slope. But what about acceleration? I'm looking at position. Acceleration is not the first derivative of position. It's the second derivative. What should I look at on the graph of the position to see where its second derivative is positive or negative? Okay, but what graphical features? So it's not just the slope. What are you thinking? Concavity, exactly. So you're going to have to look to see where the position graph is concave up, where it looks like a cup, and where it's concave down, where it looks like a frown, right? So a position, what you're looking at, because the second derivative of position is acceleration. And wherever the position graph is concave up, the acceleration will be positive. And where it's concave down, second derivative will be negative. You think you got it? Give it a shot? All right, I'm pausing this. All right, so we're going to use interval notation when we answer these. So where is the position positive? What interval or intervals? From A to C. We see that? I'm not going to include the endpoints because at A it would be 0 and at C it would be 0. So I just want to say at all the times between A and C. So we write A, comma, C. Interval notation. You've seen it, right? Oh yeah. Oh yeah, you love it. Now, where is the position negative? C to E, definitely. 0 to A. And if I want to, I could include the 0 because at 0 the position is negative. You know, at A it's 0, it's not negative. But I could include the 0. So from 0 to A, I'm going to use a U here for union. And then from C to E. When your answer lies in more than one interval, you use that between them. Yeah. Like not use interval notation. I guess if you want to. Yeah. I'm sorry. But are you okay? Isn't it so much easier to do it this way? Interval notation? Okay. Oh, okay, yeah, then fine. Okay, yeah. Yeah, this is actually so much easier. That's why I do this. Okay, let's talk about the velocity, the derivative of position. So the slope of the position graph. Where is it positive? 0 to B? I like that. It's actually, the way I drew it looks kind of positive here at 0, so I think I'll include that. Don't worry about the endpoints, but 0 to B, B is 0, so I won't include that. Anywhere else? And then from D to E. Oh boy, can't really fit that. So from D to E. I could include the E because it is still positive there at A. I'm going crazy. All right, so that's where so velocity will be positive when the slope of the position graph is positive. And where would velocity be negative? B to D. That's correct. B to D. All right. Now we want to find out where the acceleration is positive. And we said acceleration will be positive when the graph of the position is what? When will the acceleration, the second derivative, be positive? When concave up, right? So where is this concave up, Cameron? C to E, definitely. Anywhere else? 0 to A. I don't even know if I want to include that 0 because you can't really tell. I guess I will. I can. I can, so why not? Oh, yeah, I'm not taking off that. All right, so where is acceleration negative? A to C, where the graph of the position is concave down. That one I can fit. So from A to C. 0 to D for what? Oh, because this is smiling right here. It's concave up. I mean, I couldn't draw it the best, but then it goes concave down. You see that? Concave up, concave down, concave up. You know, when you're looking for a change in concavity, look for an S. You know, like right, that's where it changes. Or like going from up to down, right there in the middle, where it changes. Okay, so now we know from the graph where each of these three motion functions is positive and negative. I want to create a sign chart for this. The sign charts are going to be your best friend, you'll see. Yep, they will be. Now a sign chart, it's just a number line where you label the signs. First thing though we have to do is just make little lines at each of these values. I just might as well do that for all of them. Marks. Okay. Now, remind me, on what intervals was position positive? Was it B to C, guys? Oh, A to C? Is that true? So from A to C, what you want to do over your sign chart, in between, you want to make little plus signs. How many? I don't care. Someone's going to be worried that they're not making the right number of plus signs. I know it. You're just showing that it's positive. So the position is positive from A to C. Was that it? Where else? Was it? Okay, so everywhere else it was negative? So from 0 to A was negative. I'm going to put little minus signs. We just made a sign chart for the position. We're just showing where the position is positive and where it's negative. Looking at number line. How about for velocity? Where was that one positive? 0 to B? I can't fit too many in. Anywhere else besides 0 to B? C to E? And then between B and D was negative? Just the minus signs. And acceleration, I remember this one because we just did it. It was positive from 0 to A. Negative from A to C? Or, I don't remember. A to C? This is fun. And then from C to E was positive. Making a sign chart. Just a number line. You're indicating the sign of that function above it. Now, you'll see why it's valuable in a second. Looking back at the graph of the position, what would you say V of B is, the velocity at time B? 0. Good, because that's the slope of the position graph at time B. Everyone see that? I'm not going back to the graph. It's too hard. Let me go back and forth. When is the object moving right? For what times? What am I looking for? Which one of these sign charts should I be looking at? I'm sorry. Okay, so if you're on, does it mean because you're at a positive position that you have to be moving left or right? No, just because the position is positive, that doesn't mean you're moving left or right, so that's not the one to look at. Velocity. A particle's moving right when the velocity is positive. So, oh, I got a sign chart. I can just get the answer right from that, right? Huh? So from 0 to B. Now I know it was included at 0, but that doesn't matter. 0 to B, and then from D to E. Yes. You can look at the graph. Yep. Yeah, what I'm trying to, because eventually you're not going to have a graph to look at, you're just going to be looking at sign charts. But I want you to understand the relationship between a graph and a sign chart. And then we're going to come up with one of these without a graph. Now, if I just ask you, when is the acceleration positive? You're probably thinking, you already asked us that. Okay. But there's a reason I'm going back to it. So we already said the acceleration is positive from 0 to A and C to E, right? 0 to A and C to E. So if someone said, where is the velocity increasing? That is where it would be increasing, because any function is increasing when its derivative is positive. So if you were asked where is the velocity increasing, you'd be looking for where the acceleration is positive. But if they say where is it speeding up, that's different. It's not just where acceleration is positive. The speed increasing is different than the velocity increasing. Does anyone remember from yesterday what conditions have to be met for it to be speeding up? Riley, what do you think? They both have to be, velocity and acceleration are either both, they have the same sign. So they're either, yes, they're either both positive or they're both negative. Excellent. So now, wow, now I see why sign charts could help us. If I have a sign chart lined up for velocity and acceleration, I can now identify where this object is speeding up. Just look for where they have the same sign. In what intervals do velocity and acceleration have the same sign? That's where 0 to A. Do we agree with that one? Okay, all right, all right, I'll buy that one. So from 0 to A, Dina? D to E, yeah, they're both positive there also. Anywhere else do they have the same sign? And then B to C, very good. See, if they're both negative there, that would mean it's speeding up going left, but it's still speeding up. So when they're both positive, it'll just be speeding up to the right, and when they're both negative, it'll be speeding up to the left. It'll be speeding up either way. So I don't have the slowing down question there? I thought I did. Okay, that's fine. Now, we just created a sign chart from the graph of position. I want to create sign charts again, but from the equation for the position, because this is probably what you'll be given. So I've given you a position function, and the first thing I want everybody to do is get the velocity function. So go ahead, get the velocity, just the derivative. Yeah, it's like 1/3 t cubed. Right, t cubed over 3 is the same as 1/3 t cubed. All right, who's got the velocity function? Cameron? Excellent. Did the rest of you guys get that for the velocity? Now, I want to make a sign chart. Before I make a sign chart, it's really important to me that you understand when a function can change signs. There are only two ways a function can go from positive to negative or negative to positive. The first way a function can change sign is when it crosses the x-axis, right? It could go from positive to negative. So when it's 0. So a function can change sign whenever it's 0. Does that make sense? All I want to do is look at where it could change sign. Another way a function can change sign is when it's undefined. Suppose I had a vertical asymptote here. You see how it could go from positive to negative there? Okay. So there's no other way a function is going to jump from positive to negative It's undefined or it's 0. So when you're looking to make a sign chart for anything, first find out, is there any value for where it's undefined, like makes you divide by 0? So in this one, is there any value for which it's undefined? You can't plug in a number and divide by 0, right? It's a polynomial. They're always defined, right? Domains all the real. So they're not, it can't change signs of one of those. So the only way this could change sign is at a 0. So let's find out when this is 0. So set that equal to 0 and tell me what values of t make the velocity equal 0. Did you get form 1? Oh, that's the form 1? Yeah, because if you factor this, right, you would get t equals 1 and t equals 4. So when I go to make a sign chart, I know the only values I should mark on here, these are called critical values, the values where it could change sign. We'll get into that more later. But the only numbers I should put on my sign chart are the numbers 1 and 4. Now, every one of these starts out at 0, but it can't change sign anywhere else. So in order to get my sign chart, I just pick any number between 0 and 1, plug it into my velocity, and whatever that sign is, anyone will hear giving me the same sign. It can't change sign here. So can you guys give me a number between 0 and 1? You want a half? Okay. So I want to see if v of 0.5 is positive or negative. Now, you don't need calculators, because here's your velocity, nice and factored. If the time is 0.5, a half, is this first factor positive or negative? Negative. What about the second factor, 0.5 minus 4? And a negative times a negative? Good. I know that no matter what time I chose between 0 and 1, I'd have a positive velocity, because it's positive for 0.5 and it can't change sign anywhere in there. Give me a number between 1 and 4. 2. Let's plug 2 into our factored velocity. What about the first factor? Positive. Second factor? Positive times a negative. So the velocity is negative for all times between 1 and 4. Give me a number greater than 4. 57? Okay. I just made that one up. It doesn't matter, as long as it's greater than 4. First factor, positive or negative? Second factor? So the velocity is positive. Yes, Riley? I like the way you're thinking. Do you remember back in pre-calc when you had that you were asked the zeros and then they say, what is the multiplicity? Right? And what would happen when it was an even multiplicity? It balanced, right? So did it change sign when you had an even multiplicity at that 0? If you had an even multiplicity, it didn't, right? So yeah, that's very astute of you. So as long as your factors are all raised to an odd power, yeah, it will change sign. So don't mess up the first one, and then you could alternate. Okay, but if you mess up the first one. But if it is raised to an even power, there will be no sign change at that 0. But we'll see that eventually. Okay, now we have a sign chart for velocity. Let's go ahead and get the acceleration and make a sign chart for the acceleration. All right, this is kind of a nice, easy one to get the derivative. What's the acceleration function? 2t minus 5. Now, I'm not just going to put every single integer I've ever heard of on here. I'd be testing values for days. Where could it change sign? When is this 0? If we set this, because it's always defined, at what value of t is acceleration 0? 5 over 2. I'll put it over here. So do we all agree that the only place that the acceleration could change sign would be at 5 halves when it's equal? When t equals 5 halves? Okay, so now let's just take a test value. Give me a number between 0 and 5 halves. 1. Acceleration at 1, positive or negative? Negative. So it's going to be negative for all values of t between 0 and 5 halves. Give me a number greater than 5 halves. 9. The acceleration at 9, positive or negative? Positive. So the acceleration will be positive for all values of t greater than 5 halves, no matter what it is. Yeah. Well, it's, yeah, but for all values, even if she said 3.1, it doesn't matter what you chose. As long as it was greater than 5 halves, you get positive. Now you're going to see the value of sign charts. We made a sign chart for the velocity. We made a sign chart for acceleration. We didn't have the graph. When will the object speed up? Look at your sign charts. You got to match them up together because I can't see both mine. Look at your sign charts for velocity and your sign chart for acceleration. Remember what it takes to speed up. Riley has an idea. I don't know if it's a good idea. What are you thinking? 1 to 5 halves? They have the same, does everyone agree? Because I don't feel like looking. 1 to 5 halves? Okay. So from 1 to 5 halves, they have the same sign. All right? So it's going to speed up. Anywhere else? Yep. 4 to infinity? Is that true? Okay, good. Then I'll buy it. I like this. I just trust you guys. Yeah, I remember that. So those are the times when the object will be speeding up. So when will it slow down? 0 to 1. And then it must be 5 halves to 4 when they have different signs. Oh, how fun. See the whole value of the sign chart? If you can make one. I know it says let's go to the 24, but I just wanted to check the homework with you guys. Let me just, I know the answers are in the back of the book, but I just wanted to see if there was anything that was bothering you about any of these. Is there a number you wanted to see? You guys know you can check. Wasn't this a great one? You had to figure out which was the position, which was the velocity, and which was the acceleration. I love this one. So like, you see how the slope here is 0 and here it's 0? So the green one had to be the derivative of the blue one. And then if you look at the green one, its slope is 0 here. So the red one is the derivative of the green one. You know, usually the higher the derivative, the nicer the function is. It gets, you lose a degree every time. So it went position is the blue one. The green one was velocity, and then the acceleration was the red one. I like that one. It's fun. Did you have any other questions on any of these? What about that one where you had to graph the speed? Oh, did that confuse you, the wording in 23? It said find the acceleration each time the velocity is 0. So you had to find the times that made the velocity 0 and plug them into the acceleration. No? Ah, it's okay. No, the one thing I thought you might have trouble with is an 11. When you had to graph the speed, and I just want to do like pretend all these other colors aren't here. This was your velocity in black. The speed graph, which I tried to draw in green here, looks the exact same when the velocity is positive. But you see where the velocity is negative? Speed's got to be positive. So all I did was I just flipped the graph over the x-axis there, to make it positive. So the speed graph is what it's all highlighted in green there. Oh, yeah, you can always graph the speed by just leaving the velocity graph alone when it's positive and reflecting it over the x-axis where it's negative. Then you got to graph the speed. Oh, they hate this. All right, so forget about that. Oh, yeah, we could do that. I wanted to do one more problem with these. That's awesome. How far did we get in example B? I think we got up to the table, then we couldn't do it. What did we get on B? Yeah, we didn't actually get the distance, though, right? Oh, we did get the total distance? What? You guys are... Oh. Oh, okay. You got it? All right. Let's just do one from scratch. This would be a good one. Let's just see if we can get through example C. That's a fun one. So this one, in example C, we're looking at a graph of the velocity. What? So, move stuff. So, we're looking at a graph of the velocity. Oh, man, I'm covering stuff up. First thing they ask, and I think this got cut off on yours, they ask us for the average acceleration on the interval from 0 to 8. I think that's missing on yours. So still yeah, the 8 is missing. How do you get average acceleration? Say it again. Change in v over change in t for average acceleration. So we're going to have to get v of 8 minus v of 0, right? Because it's delta v over delta t over 8 minus 0. How am I going to get v of 8? Oh, yeah, read the graph. What is v of 8? 0. Oh boy, it's starting. So v of 8 is 0, and, oh, that's better. What's v of 0? 1. So the average acceleration on the interval from 0 to 8 is negative 1/8. Because if I connected the start point and the end point with a line, it'd have a slope of negative 1/8. So we got that? Average acceleration delta v over delta t. Uh-oh. Next question. So that was average acceleration over an interval. Now we want the acceleration at a particular time. We want the instantaneous acceleration. What are we going to use to get that? dv dt, the derivative. How am I going to get derivative from a graph? What do I have to look at? The slope. So I got to take the slope of the velocity graph at time 2. What does it look like? I know I'm not the greatest artist here, but what does it look like the slope of the velocity graph is at time 2? 0. Boom. Got it? So it's 0. No, don't start doing this to me. It's like a cycle board. I was going to say if I press hard, it's better, but I guess that doesn't really work. All right? So kids at home that can't, look at that. This is what they got to see. It's 0. All right, I'm just going to say it. It's the slope of the velocity graph at t equals 2. That's how we're getting to 0. I'd love to write it, but it's going to be a mess. Now, this is the velocity graph. Oh, there. This is acceleration at time 5, positive or negative? Because you're looking at the second derivative and you're thinking it's concave up. Okay, the problem is that's not the position graph. Acceleration is not the second derivative of that, is it? First derivative. So we don't look at concavity. What do we look at? Slope. So I know. I was like, I just led you into the trap. That's what I did. You got it here. You know, you knew acceleration at 2 was the slope, and then, oh. All right, so is acceleration at time 5 positive or negative? Negative, because the slope over here would be negative. It says approximate when the speed is the greatest. Remember, the speed will look the same as velocity when it's positive, but you flip it up wherever it's negative. At what time do you think the speed is the greatest? Yeah, what is the speed at time 6? It's 3. So a t equals 3. I'm 6. I'm sorry. T equals 6. The speed will be 3, which is the greatest. So if you thought it would be a 2, no, the speed here is only 2. When does the object change direction? Now, this is the velocity. When velocity is positive, it's moving right. When velocity is a negative, it's moving left. What should I look for to see when it changes direction? When it's got to cross, right? When it's 0, but it's got to change sign. So a t equals 4. So you're looking for the velocity to change sign to see where it turns around. On what intervals is the object moving right? What do we know about the velocity when it's moving right? It's positive. So where is this positive? 0 to, I'm thinking 4. I don't think increasing. It's just where the velocity is positive. And when is it moving left? 4 times? 4 to 8, where the velocity is negative. When is it speeding up? So when is velocity, where is velocity positive and the acceleration positive? So it's got to be above the x-axis and increasing for both to be positive. Yes, Riley? 0 to 2, they would both be positive. Anywhere else where they have the same sign? Because from 0 to 2, the velocity is positive because this graph is above the x-axis, and acceleration, its slope, is also positive. So if it's positive and increasing, we'll be speeding up. Ryan? 6 to 8, well, the velocity is negative because it's below here, but the slope's positive. And we're looking where it's speeding up. Yeah, how about 4 to 6? They're both going to be negative. So if it's negative and decreasing, or positive and increasing, it's going to be speeding up. And when would it be slowing down? When would velocity and acceleration have different signs? 2 to 4, and 6 to 8. And that's what we're doing today. You guys are good. Why is it? Oh boy. It's not letting me pause it.